So I will be starting with this special session that is about data-centric computation. And what we mean by this is basically that we try to push the focus a little bit towards the idea that data actually is what we care about, and then computation is needed to digest the data, versus that we think that data is just the byproduct, needed to feed in input and kind of generated as an output. It really is the core of our efforts. Okay, in my talk, I will be specifically talking about the potential for IO-aware workflows in climate and weather, but I will also go a little bit beyond this, talking about the general vision. So let me briefly introduce a little bit climate and weather workflows. Firstly, let's assume you have to simulate hundreds of years in the future the climate. So, and in every month of this model time, you want to perform certain workflow operations, like you want to generate, for example, the median values over certain area in the world, and then store this as an output. So those kind of sub workflows that appear cyclic, for every month, they should be executed. And the scientists have generated a specific software for that called Silk, developed at the Met Office, that allows to represent such a cyclic workflow. On the right-hand side here, can you see the mouse, by the way? Yes, I suppose. Yep. You can see such a workflow where we have for every month different types of operations. And this kind of workflows, they can be really deep. So we're talking about 10,000 nodes, and that's why they really needed a specific software. And such a workflow can be encoded as a simple text file here, in which you contain the different tasks, you give them some names, and specify the commands to execute. And then you can define environment variables that you want to attach to those tasks. For example, you may say, this task, I want to run it with 200 nodes. Okay, and of course, a workflow, this is just an example. Toy workflow here, like I said, is really huge in a general sense. So let's talk about how such a workflow is executed. So the scientist has specified this workflow configuration file and the commands to execute. Such a command could also be a script. And he has provided these environment variables that could be like the file names they want to use. And these kind of information may depend on the specific cycle. So you may want to write, like, the output is the current month, for example. Okay, all this is encoded. The scientist talks to Silk and says, okay, I want to start this workflow. And now Silk scans the workflow and generates jobs for it and injects it into the workflow manager, like Slurm, for instance, that you may have. And the workflow manager then is in charge to make sure that the order of execution is as expected, but Silk will also monitor the execution. And finally, the job is, an individual job of such a workflow is dispatched by the workflow manager, running the script, running the applications with the prescribed input and output. So as we see in this example, and by the way it is defined, the scientists really talk about tasks here. They are not thinking about the data. The data is implicit. So if this task here kind of generates some output that is later needed for the production, then this information is really implicit, communicated through the graph. So such a workflow is then executed on our data center, of course, also kind of going into the cloud. And as we know, the data centers, they nowadays look a bit more heterogeneous. We have nodes that have different memory and storage characteristics, and also have different shared storage technologies, even in-memory storage characteristics. And if we think about one single application that's executed, particularly the weather or climate model, then this may have a very deep software stack seen here on the left. And the scientists use a specific software that actually is kind of a burst buffer in the application side to accelerate the I/O. And under the hood, they use typically a software like NetCDF, for instance, as a middleware. So this is kind of the starting point where we connect to with our Earth System Data middleware, which is part of the EasyBase Center of Excellence in Horizon 2020 project. So where we kind of changed the NetCDF backend from HDF5 aware to a more, I would say, modern approach. So the ESDM, in short, provides a transitional approach for our general vision for I/O, for scalable data management. It addresses this inhomogeneous storage stack, and particularly wanted to address efficiency and make sure that applications can achieve performance portability, so that you don't have to tweak in this deep stack, all these layers depending on the specific machine that you run. So that was basically a background. In the EasyWays project, we have more than 20 stakeholders representing the European community in climate modeling and numerical weather simulation. And the goal of the EasyWays project is kind of to make the efficiency and productivity of high scalable, really big simulations possible. And that we target to achieve demonstrating applications with a 1 square kilometer kind of resolution. So now let me leave for a moment this topic of climate and weather, and let's talk about my general perception of the data center and how we actually submit at the moment grants and run projects on it. So if you submit a proposal to a data center, you typically provide some information like the time you need, the CPU, GPU hours, and storage space. But once you kind of have this proposal granted, well, as a scientist, you can basically do what you want, right? You log in with SSH and you do run your jobs. And there is some limitations imposed, right? Compute limits you still have and quota. But from the perspective of a data center, we don't know what's going on in terms of workflow, what's really going on, and what is the intention of the scientists may have. And that is often a problem when it comes to procurements, right? Because then the data center needs to really find the representative applications and kind of make sure that they are included in benchmarks. Also, I would say that in a data center, we still use tools that are working with 40-year-old concepts. Yeah, I'm a bit provoking in this point. But if I look and speak with some physicists, right, I'm really surprised because they sometimes run experiments that they've planned a couple of years in the past. Then they build up, all this hardware. They ship it, they plug it in, and it, well, with very tiny adjustments, pretty much works. And they have a dedicated time slot to do that in the future. So, and that is totally different from my perspective from a lot of scientists that just, log in with SSH where they type in these commands. So the question is, can we utilize this workflow information better? And that brings us to the vision, the high-level vision first, right, before we come back to climate and workflow. I personally strongly believe that the scientists should, think about delivering these workflows that they want to run in a very abstract, high-level fashion. And they ship, of course, the containers, they ship the data management plans with the data life cycles, and they provide even time constraints and a potential budget they may have. And you give this kind of package to the data centers or vendors, right? And they make you an offer. They could, they could simulate your workflow a little bit. They could estimate the cost, energy consumption, and they could figure out what is the best option to run, right? Maybe as a data center, once you see, oh, there are coming in so many requests that, have this particular requirement for storage or compute, well, maybe I should, focus more on that. From the side of the system, if you have the workflow information, you can maybe exploit it to orchestrate the I/O, make decisions about data location and placement, and maybe even trade compute versus storage and energy cost versus runtime, and all those kind of fancy optimizations, I would say. So I would say, in terms of usability, big data is a little bit ahead of what we can do in HPC at the moment, and I hope we catch up to get a more flexible dynamic environment. Okay, and with the provoking part, coming back to a more realistic next steps. So what we do now in the EasyWays project, our idea is, or vision that we are going to implement, is that we exploit the workflow knowledge. So first we enhance the workflow description with I/O characteristics. So what input do you need for this task, of course, and for outputs, what kind of characteristics is the data that you produce. Also, we annotate a little bit about the information life cycle, And by doing these changes, we come from these implicit input-output dependencies to an explicit machine. So we know in advance what kind of stages the program will be in and what kind of data is needed and generated. And it gives us the opportunity then to do smarter I/O scheduling, considering the hardware and software environment, so that you could, in terms of data placement, you could do, for example, data migration, data staging, replication, in general, in a more optimal fashion. Also, in terms of data reduction, of course, we could apply suitable data compression depending on the precision needed by the user. And we could, like I said before, trade computation versus storage space. For example, by just storing the checkpoints, and later when you need the data, you go to the specific checkpoint, run the simulation again, I don't know, for a month, for instance, and produce the new output that you may need. And by that, we kind of really drive forward the separation of concerns, such that the scientist declares the workflow, including the I/O, and then the system will map the workflows to hardwares using knowledge from experts, but also, I strongly believe, in machine learning, because the systems nowadays are way too complicated than a single person could optimize it for. Let me show you some examples. So in the terms of extended workflow description, here we see 3 cycles, and we see, instead of just the blue tasks, we see these yellow data sets that go in and go out. And sometimes between the cycles, like here, we have the dependency because the checkpoint needs to be fed into cycle 2. And I will, in a moment, then present to you the characteristics when we come to the specific design, but not for now. Okay, so how can we try to exploit this? Here is an example. So consider that we have 3 file systems. We have a node local storage, which could be SSD or what have you. We have a scratch space, a global scratch space, but it is purged after a while, and we have a work file system. Maybe you have even multiple file systems, like D2Z, for example, has 2 file systems. And now we have to make the choice as a scientist normally where to store the data on those 3 storage systems, right? So here's a timeline for how to place a single data set. And you can see at the beginning, I may store it, for example, on the local storage. Later, I migrate it to the work storage, where it is read a couple of times. And then I maybe delete it after a couple of months, years, or what have you. And there are alternatives possible that you can see here. And many more are really that could be envisioned, depending on the hardware and software that you have. And at the moment, the users have to think about their workflow and then to generate their own life cycle for the individual data products. And well, I think it's not a secret that usually when a human does such a kind of optimization, it is probably not optimal. So that brings us to design. So what do we, from this vision, actually then implement? How does this fit in existing components? So first of all, we have to, again, configure the system information, know about the data center. Then we have to extend the workflow description, and then we have to do the smart I/O scheduling. So here on the right, you see the modifications that we do to the execution. So the scientists now have to define not only the workflow configuration file, but also a workflow I/O configuration file. And we particularly made this, what I present to you, disentangled from the current software, because the software like Silk, that has very long development cycles. And what we do here is more to generate some kind of prototypes that hopefully in the long term will be integrated into such a software. That's why we want to really make a very loose coupling. Okay, so we have the I/O configuration file, and then in terms of Silk, there will be modifications made to call this scheduler and figure out from the scheduler some kind of Slurm, additional Slurm information like priorities and directives that then get injected into the user script. And once the user script runs, it again spawns the application. The application should use ESDM, our middleware. It loads the configuration file, which I will introduce, which is kind of containing the information about the system. Likewise, the scheduler will also use this configuration file. Okay, so the communication in terms of information between the made choice, between where to place data, and then to actually enact such a behavior, that takes place within the script. So when we generate the file names, we now basically they are not anymore file names. They are basically pseudo file names that not really exist anymore due to the way the middleware works. And we will extend this description of the file name by providing a suffix that encodes then the prioritized choice for the data placement. And this information then is read by the ESDM inside the application and basically enforced when it makes the choices how to use the data placement. Okay. Well, talking about the system information, so ESDM already has a configuration file in which we have for different storage targets. Here we see Luster 01 and Luster 02. We have a simple performance model that we are extending as part of EasyWays 2. And we have information how to use it best, like how many global threads should we use in a parallel application, how should we fragment the data, how many threads per node, typically a good configuration. And this information is used by ESDM. And in fact, ESDM can split a single data set across multiple storage locations. So that means we actually achieve better performance at DKZ because we have two file systems, two Luster file systems, and we use both at the same time. And the user doesn't even realize that because all of that is controlled pretty much from this system information. So you could also use node local storage, but of course with node local storage, we have the problem when we run a workflow, we have to dispatch any kind of usage of the same data onto the same nodes. And that's again one of the reasons why we actually chose this strategy, because Silk actually knows the whole workflow. And this workflow could run, for hours, for days, or sometimes even for weeks if it's a really long workflow. So it's really beneficial to exploit this long-term information than just looking at a single application optimization. Okay, talking about extending the workflow description, well, we choose to have a similar file. It's a modified ini format. For each task, you specify pretty much the inputs needed, which are all pretty much pseudo file names, but it could also use real, like netcdf file names that are then dynamically mapped. From this, we kind of compile a virtual container for this application that only sees what it needs to see, disentangling from the actual storage hierarchy name system, file system. And then in the output for each variable, we kind of can specify some information like the lifetime, the size, and also in particular, like the precision. If you think about compression, lossy compression, there are different quantities that you could specify. Here we just specify one quantity, which is absolute tolerance in terms of error. Like this could be 0.1 Kelvin, for instance, if the file stores if the dataset stores information in Kelvin. Well, this is just an example how we envision it, how it in detail will look like, the language we have to look at, because we figured it's not easy, as this has to be written by computational scientists, so to speak. We have to be really cautious about the language used. So the Smart I/O scheduler then provides hints, like I said, for Slurm, in particular for co-locating tasks. And this will be also, what we use also is we use IME to pin data to the cache or prefetch the data to the IME system from a Luster backend, so to speak. And we also optimize the initial data allocation. So when you have the cyclic workflow, what you could think is in cycle 1, I place the data on Luster 01, and in cycle 2, you place it on Luster 02. This is a very simple example of how you could potentially optimize this. Also, you might want to really use the local storage that is available in the nodes, because for extreme large runs, which we have with this 1 square kilometer accesses, if there is local storage, this local storage is typically higher performant because you have thousands of nodes. So, and as I said, basically what we deliver as part of the project is we only deliver the things that really benefit the climate and weather applications. But all of those things, I hope, deliver to this long-term vision that I have in mind. So let's really recap. The goal of the vision and design is the separation of concerns between the developers, the users, and the system optimization. The scientists should enhance the workflow description with I/O characteristics. They should provide, this generally high-level idea of a workflow that ultimately inputs nothing or very tiny data set and generates at the end scientific output. That is for me the would be the ultimate workflow. The Silk part is a subset of it. And the system then exploits this workflow specification by considering the system characteristics, particularly as in the future we have heterogeneous machines, I would say only, because it's more efficient. So, and if we have that in place, I think generally we have opportunities to exploit this workflow information further. Like I mentioned, from the data center perspective, you could do performance modeling. You could, if you include the computational model as well, how long would the different processes run on a given architecture and so forth? How much would it cost on a given platform? And you could play with what happens if you have a different storage system and environment. And I would wish, or I personally think, I may be convinced otherwise, that in the long term, instead of just asking for a certain CPU amount and making, a math, I need this CPU hours, I need this storage space for this and these reasons, I really wish that we have this high-level, workflow description that needs to be submitted by the scientist, and then the data center can say, oh, yeah, this looks really great. However, I mean, DQZ, isn't perfectly well suited to run it. If you go to, another site, this site X here, actually it would be much more price competitive. So I think that ultimately, given that we have nowadays the cloud dominant and takes away HPC resources, I think this focus towards more cost efficiency is really important. So that's my talk. Thank you very much.
Thank you, Julian. One question.
Okay, I see here are questions. Actually, oh no, this is solved. Have you already tried to compare your IO-optimized Silk workflow with already existing real-life large-scale problem? No, we haven't done that. We have all the stakeholders from the climate community and the kind of developer stakeholders of Silk on board. And it is a lengthy process, like I mentioned, particularly in Silk, to change the way it works. But we know from doing performance measurements the kind of strategies that we want to perform. And I'm sure we will see some benefit for those cases. I'm not aware if Silk has any kind of validation of the workflows. In particular, I mean, I know it has lightweight checks for sure to make sure that there is, some basic consistency guaranteed. And the last question is, how about Kubernetes? I would agree. I mean, I think, the way in terms of HPC where we schedule exclusively resources to compute, I think at some point this will go away, and we will truly try to co-locate and co-schedule multiple applications on the same nodes for efficiency reason. And I think Kubernetes is a good example that will enable that, but it's a different talk. Okay, that was the question here, right? Thank you very much. Have a good day.
Thank you, Julian. Thank you.